Okay, today we're going to talk about so-called finite volume method. So far we've been considering some issues related to finite difference method. So finite difference method basically is a way to approximate derivatives in our differential equations. So we have a set of points, grid points in some certain direction, say x, and we have values of some function in those grid points separated by some distances, and we use Taylor series basically to to expand function in a certain node using values of function in a neighboring nodes. So it's all about nodes. We basically approximate functions in our differential equation, like, I don't know, phi dt plus u d phi dx, df dx. So we approximate these derivatives in certain points, and then we use Taylor series and approximate derivatives using those grid points. So it's all about derivatives. And because derivatives is basically a concept that involves differences between grid points, some limit of delta y, delta x, that's why this method is called finite differences, because they're not actually going to zero, they're finite. But finite volume method does not operate so much with nodes, but more switches its attention to cells. So in one dimension it would be so we have still this kind of nominally values, but now we divide our region into cells, and each value is actually defined in this cell. So for example, we can assume that this value is just constant within that cell, or we can use some, I don't know, some linear function in that cell, but we operate with some we actually approximate value of some function inside the cell as a whole. And then cells are made interact to be, at their borders or boundaries. So there are some fluxes that connect those cells together. So cells exchange some variable, some material, some mass or energy or whatever between them through these fluxes and their boundaries. So that's different approach. In one dimension it looks kind of similar, but actually it looks similar to finite difference scheme written in a flux form. When we talked about last couple lectures about conservation, we actually derived equation in so-called flux form. And there you have this kind of fluxes concept appear. Here there are no fluxes, this is just advection or transport of some quantity. So if you wrote it like this, then it's completely different, conceptually different framework, because here now you have derivative of some flux. So, so this is basically kind of basic conceptual difference between finite difference and finite volume. So basically, finite difference operates with derivatives, and finite volume actually switches to some integrals over some region or cell, and reduces problem not to derivatives in some point, how to approximate it, but how to approximate, but it reduces to volume integrals and surface integrals of fluxes around the surface that surrounds the cell. So in one dimension it's just one point, that's where fluxes interact. But if you have, say, two-dimensional area, so this is your volume in two dimensions or area, and then there are fluxes that go through that boundary between boundary of that volume or that area, and this integral along that boundary, this is what finite volume method is all about. So how to find this, so it reduces differential equation to so-called integral equation, and solves integral equation instead of differential equation. So let's switch to some example to understand it better. So there are many various various approaches to finite volume method. So basically, finite volume methods, it's integral method. So you switch to integrals instead of derivatives. But you can approach this using different methods. So there are several distinctly different approaches to finite volume methods. So the first one we're going to consider, I kind of like, but it has its own problems, although conceptually it's kind of simpler to understand. So first let's consider one-dimensional case. So one-dimensional case. So for finite volume method to work, we need to integrate something, the equation. We need to integrate differential equation. But of course, if an equation is written in advective form, it's very difficult to integrate. Like the terms like u, d, f, dx, it's how you integrate it. You need to know both u and f to integrate it analytically. So we should be able to integrate it, and the simplest way to integrate some function is to integrate derivative of a function, right? So integral of, say, df or df dx over dx on some interval from a to b, you know, it's equals to antiderivative. So in this case, it's f evaluated at points a and b, so that it's equals to antiderivative at b minus antiderivative and a. So you know that from calculus. So you see how easy it is to integrate derivative. You don't really even need to know how this function changes in between 2 points, a and b. Well, it can be this, it can be that. What matters that this integral actually depends only on values of that function in point b and a. And that's what finite volume method is all about. It just uses some different. So this is true. This is so-called Leibniz rule. It's true for 1 dimensions, obviously, but how you generalize it to 2 and 3 dimensions? For that, other theorems are used, so-called Stokes theorem, or in 2 dimensions, it's actually Stokes theorem in 2 dimensions. It's better known as a Green's theorem, and in 3 dimensions, it's just full-blown Stokes theorem. It's basically the same statement, but in 3 dimensions. So something that reduces integral over this interval to basically boundary conditions. So in 2 dimensions, it's going to be not just this value minus this value, but it's integral along the boundary. So let's consider in 1 dimension. But we should be able to write our equations in this form, in form of derivatives only, which is, in our case, in our field, in fluid dynamics, it's writing equations in a flux form. So, for example, in 1 dimensions, equations look like the following, the dynamical equation. It's like du dt plus, so this is original equations, momentum equation, let's say in 1 dimensions, compressible flow, equals to minus, so it's 1 over rho dp dx. And then we have continuity equation, d rho dt plus plus d dx u rho equals to 0. So these 2 equations are written in advective form, and so you can integrate this equation, because here you see it's derivative in the form of derivative of a flux of mass, but here it's not. So, but last lecture we actually discussed that, how to convert this equation into equation in flux form. So you can write this equation as d dt rho u plus d dx rho u equals to minus dp dx. So now you see it looks like in flux form. So now you can actually combine into one variable, like this equation. You define some f as, by definition, as rho u plus p. Then this equation, and you use like some function, which is rho u, by definition. So then this equation will be written as df dt plus df dx equals to 0. So you see we converted kind of, this is general form of our problem in one-dimensional case. So you see it's rate of change of some function equal to some other function, derivative of that with respect to x. So you see this one is now has a flux form. So there is it can be easily integrated. So now let's consider grid and divide it into cells, so that this is a cell with size delta k. So this is just size, this minus this. This one is delta k plus 1. This is delta k minus 1. So this cell will have index k plus 1 and k minus 1, and these boundaries will have indices like k minus 1/2, so in the middle, and k plus 1/2. So this is, our f is defined inside the cell, and f's, because its differences, are defined at the cell boundaries, and f defined in the middle, but not in a specific point. So how so for that we defined some average f. This is what is defined here. And average, if we talk about first order kind of derivatives, of course we could use some polynomial if we want. But let's consider this simple case. We defined just cell, everywhere is the same value of f, which is equals to average of actual value of f. So we define f mean as normal way using integrals. It's integral from x k minus 1/2 to x k plus 1/2, or integral of f dx of that integral, and divided by, so it's integral of dx and divided by size of interval delta k. So delta k equals to just x k plus 1/2 minus x k minus 1/2. So now let's, so this is we can define this, but now let's apply it to this integral. So now let's average these equations, this equation. So we integrated from xk minus, so we kind of average using this averaging operator. So if we do that, we have d dt, and of course t does not depend on x, so it can be taken out from the integral. We have 1 over delta of delta k, and here is integral xk minus 1/2 to xk plus 1/2 f dx, plus, now integral of df dx is of course equal to f at this point minus f at this point, because you can integrate derivative as we did before. So it equals to 1 So it equals to 1 divided by delta k, f k plus 1 half minus f k minus 1 half equals to 0. So now this guy is just equals to this. So our finite volume representation of this equation becomes d dt of this f in the grid cell k equals to minus f k plus 1 half minus f k minus 1 half divided by delta t, delta k by the width. So it's basically this flux minus this flux divided by delta. So this is exactly looks if we used finite difference method, but to the equation in flux form. So this is flux, like we did in a couple previous lectures. It's flux in this point minus flux in this point divided by distance equals to value in this point. We assume that it's just one point, but here this mean f means that the whole cell has this value. But conceptual equation looks exactly the same. So in one dimension, finite volume is actually the same thing as finite difference method. It can be, equations look very the same. So looks like finite difference method in flux form. So, so this is 1D case. So 1D case is not really, one-dimensional case is not very interesting in this regard, because it doesn't really show what finite volume method is, because it just finite difference in when you apply it to equations in flux form. And then you basically use your finite difference approximation to using Taylor series, using approximation for these fluxes. You can use first order approximation, you can use second order approximation, third order, using all these values of f and so on. And that would basically be all about how you approximate now your fluxes at these boundaries, which information you use for that. But conceptually it's the same problem as finite difference. So there is no really advantage of finite volume method or anything new finite volume would bring to one-dimensional case. So when actually finite volume, when does it actually shine? Of course in two-dimensional and three-dimensional case. And in our field, usually finite volume is applied to two-dimensional equations, even if it's three-dimensional system. Because in our field we have like a flow, like say atmosphere, and horizontal kind of what's going on in horizontal, we tend to treat differently than what's going on in vertical, because in our field horizontally it's kind of our turbulent, well, our flow in atmosphere is very anisotropic, or not the same in horizontal or vertical direction. In horizontal, like we have all these kind of beautiful cyclones and other things. In vertical, it's different kind of. First of all, the scale is very different than horizontal usually, and it's usually shallow kind of atmosphere, because it's only say troposphere is only less than 20 kilometers high. Like something like 15, and horizontally the scale of phenomena can be hundreds of kilometers, so it's very kind of not isotropic. So finite volume method is usually in atmospheric models, and ocean too, applied to horizontal directions, and vertical directions usually handled with finite differences, although written in flux form. So this is basically still used in vertical direction. But in horizontal direction, in our models, we use finite volume methods. They are much more popular than finite differences in our models. And one of the reasons is because finite volume methods allow you to handle very complex grids. So it's very nice and easy to use finite difference method when you have your grid clearly follows some direction. say, direction x, and here you have direction y. So you have this regular grid like that. When you have grid like this, of course, finite difference methods are just way to go. It's simpler. So you have x direction, here you have y direction, and you see all your points. You have clear derivative in this direction approximated by points in this direction in this, handled by this direction. Very easy to expand in Taylor series along those directions. So when you have regular Cartesian grid like this, finite difference method has its advantages. But what if you have grid like this? So you have to model some flow in a channel or something. And what do you have like this? So your coordinate system is still like this. But now you see everything is like, this one is not clear. You cannot compute clear, say, what's derivative in x here? X direction, say, in this point is this, and y is this. So, but you have points here and here. So, and here, how you actually approximate derivative in this case? Like df dx. What's df dx? How you use Taylor series for that? Because you have now, variation of function you need to take into account even when you compute df dx, that it varies in y2. Your next grid point that you try to approximate is not actually there along the x-axis, it's somewhere else. So what you do in this kind of case? Moreover, what if you have some grid which is actually like consists of triangles, like let's say you have some obstacle here, and then your flow is going around it. So you have grid something like that, which is very dense, close to your obstacle, and then becomes like this. And you build it using like triangles like that. What if you do like this? Some irregular grid, and so on. How you approximate derivative in this case? How you use this equation in this form, or even this equation? How you approximate derivative? So that's where finite volume method actually is the only basically way to go, only practical way to go. So for that, let's consider two-dimensional case, and one of the methods that is based on using Green's theorem. Okay, so now let's consider two-dimensional case, which is much more interesting than the one-dimensional case. So for that, we need to be able to write our equations into the two-dimensional equations in flux form. So we assume that our equation for some quantity f looks like the following: df dt plus df dx plus dg dy equal, I don't know, some right hand side, could be some other terms here that don't have form of this kind of derivatives. So let's say that it's called g. Oh, can be 0, but let's be more general. So we should be able to write our equations in this so-called flux form. So to give you an example, let's consider some kind of prototype problem that usually we may deal with. Like for example, this could be momentum equation. Like for example, in the flux form, dimensional momentum equations would be written like d rho u dt plus d dx rho u plus d dy rho uv plus dp dx pressure gradient, and equals to, say, I don't know, Fv Coriolis force times rho, and in some diffusion, like in the following form, like plus d dx of some stress in the x direction for horizontal momentum, so it's like tu x plus ddy tu y. So advection, pressure gradient, Coriolis force, and divergence of diffusion flux. So in that case, our F would be what? It would be rho uu plus B and minus tau ux. G would be rho uv and minus tau uy. And our G would be our Coriolis term, FV rho. So that's basically, we see that we can view this equation in this form. Or like another, for example, if you have advection of potential temperature, like d rho theta dt plus ddx rho theta, so it's in flux form, u plus ddy rho theta v equals to convergence, divergence of subgrid scale or diffusion flux. So it's a ddx. Here you have say flux of theta in x direction. I won't specify them exactly here, just for notation. So it's divergence of some heat fluxes in x and y direction. So in that case, F would be rho theta u minus F theta x, and G would be rho theta v minus F theta y. And it would look still, and G would be, in this case, like for example, here we have radiative cooling, rho q rad. So this rate of change of temperature due to radiation, so G would be rho q dot rad. So you see that basically all our equations can be, in our field, at least in atmosphere, can be written in this form. Okay, so now let's apply finite volume method. For that we need to integrate. So how we would integrate here for two-dimensional case? Well, we define first our mean. So F mean would be 1 over, well, first let's define grid. So we have, let's say, some arbitrary grid in this direction, like in x, y, something like looks like that. And we have coordinate system that looks like this. So you see that our grid is not nicely collocated. Direction of that grid is not the same direction as our coordinate system x, y. So we have these values of all variables, say, defined, let's say, at grid nodes and these intersections. And we can count them very easily in this case, because it's regular rectangular, kind of, not rectangular, but actually it is rectangular, but it's not right angles here, so everything is kind of like a little bit skewed. So it's, but we can count them anyway. So we use index I in this direction and index j in that direction. So if you can use arrays to count your variables, two-dimensional, three-dimensional arrays, then this grid is basically very well structured. You can easily, if you can count all your all grid points using arrays, it's very simple to code. But it could be, of course, some irregular grid when, like, say, grid like that. For example, something like this. Then it's not easy to count, like if you have variables in the middle, let's say here. How you would use array, because this grid cell can have only a certain number of neighbors, let's say 5, 6. Here this cell can actually have maybe 3 neighbors or 4 neighbors, and so it's impossible to actually use arrays, 2-dimensional, 3-dimensional, or whatever 1-dimensional arrays to actually count all these cells. So for that case, you need to use so-called linked list. So you need so each grid cell actually has a list within that cell that keeps coordinates of its neighbors, let's say. So when you know this grid cell, actually you know its neighbors, but you cannot know it's like up front. Just so for compiler, when it compiles your code, it doesn't really know anything about your grid. Like when you supply it with array like that, the compiler, for example, compiler can actually create a very efficient code how to access to all these array elements, because it's very regular kind of structure, memory structure. So compiler can actually optimize this access to all these cells. Here it's a little bit more tedious for compiler to upfront to optimize this access. So it needs to do it while it's executing. And executing your program, and that's why this kind of grid structure, which can be this is kind of unstructured grid, and this one is structured grid. This grid would be always slower for computers than this grid, because of it cannot predict upfront which memory cell it should access next. So that's but conceptually this equation can be applied to this grid or to this grid with no conceptual no difference. So now let's just for simplicity, let's consider this grid. And now we need to, in finite volume, we need to define our volume. So in this case, in two-dimensional case, volume is some area, so or cell. So we need to define two-dimensional cell. So let's just basically use middle of this of these edges of those big grid cells to define our control volume or our control cell, like that. So this is our grid cell, and now this cell has area A, which we can pre-compute or compute before actually computation, so to save some time. So now we can let's define average like we did in one-dimensional case, average over the grid cell. So average over this quantity f here is equals to 1 over area, double integral of f dx dy, and this double integral over this area A. So this is formally, we define it like this. So now let's apply this averaging operator to our equation in this flux form. So we will have, well, I immediately write it, df dt. So this one is area, say ij. This is ij. This is ij, ij. This variable ij. So we have df ij dt plus. So now we integrate this guy. So we now just write it formally as integral, double integral of this area of df dx plus dg dy dx dy and equals to this just g average, right? Just average this function. So what we need to evaluate is this guy. Because here to find this was df dx, as I mentioned before, because your coordinate system is like that, your df dx in here is kind of, because this grid is tilted on any direction. It's not clear how to evaluate these derivatives using this grid. If your grid again was regular, aligned along x and y direction, then it would be very easy to evaluate those derivatives. But here the grid is not aligned with your coordinate system. So for that we will use Green's theorem, which is just a two-dimensional version of more general Stokes theorem. Stokes theorem, which is three-dimensional statement. So here we use Green's theorem, which says the following. So Green's theorem. It says that integral, double integral over the area A of expression like df dx minus dg dy dx dy. So here you see this minus sign here. So it's if f were like v velocity component in this direction and g was u velocity component in this direction, it would be like vorticity. So it's like integral vorticity, and this is not coincidental, because Stokes theorem on the left hand side here, it's integral over volume, but it's curl over vector. Curl, it's like vorticity. Say if velocity, if f and g is velocity components, then it would be just vorticity. So it's curl of some vector and equal. So in this case, in a Green theorem, it's stated like this, and it equals to 1 over area integral this contour or this this integral over all this boundary of of f dy minus g dx. So you see here f was with x, but now it becomes with y. And here in Green's theorem and in Stokes theorem, it's very important to choose correctly the direction of integration. So actually for areas, for Green's theorem, they correct this when you compute this integral. It's important you can go two directions, like this direction or that direction. So counterclock or clockwise direction. So for Green theorem, you need to choose counterclock direction. So your direction of integration should be like this. And it is important to compute integrals like that, in this direction. Otherwise, you will get negative sign. If you do it opposite, then instead of positive like some sign, you will flip the sign of. And of course, it would make a difference if you flip sign here. So, so this is a Green theorem, and we now need to apply it to this. But here we just replace, you see, g with minus g. So if we replace sign here, we arrive to Green theorem. It's minus, and here it's plus. This is Green theorem, so it should be plus here. So now we just can define g equals to minus g, doesn't matter. So we just change this sign here, and we need to change sign here. So this is our Green theorem. And now if we apply it here, let's multiply by area. So we will have A ij df ij dt plus this integral over control integral over, and here is going to be f dy minus g dx equals to this average g ij times also area ij. So you see, we switched from necessity to compute all these derivatives, which we don't know how to compute on this grid. We switched to these integrals along these things, no derivatives here, like per se. This is our fluxes times this dy dx, and those are total derivatives, you see. So it's not like, even though it's two-dimensional case, dy does not mean that it's changing y with constant x. X, when you compute dy, is also may change. So only on a grid which in the same direction as your coordinate system axis, xi, these dy and dx is like similar to, so dy is taken at constant x and dx taken at constant y, but here they're actually changing. So now we need to write this in finite in some difference form. So we need to evaluate this integral. So integral is basically summation, right? So we need to replace this integral by sum of, in this case, 4 integrals. One integral along this edge of this cell, then this edge, then this edge, and this edge. We add all 4 of them, and then we get our estimate for our integral. So so let's for that, let's first define our dy and dx in this case. So it's easier if we make some notations here. This point, this corner is going to be A, this corner B, C, and D. So this integral is just sum of some f along, say, for AB, it's some f along this AB edge times change in y. So it's y in B minus y in A. That's what D means, delta. We replace D with kind of finite differences of y. So so how we defined f's? We can. That's what basically would be all the whole difference between various implementations of this method. You can use first order approximation for f's. You can use second, third. You can, like, in order to find this f along this edge, you can use like some neighboring f's. But we will assume that our fluxes are actually defined in the same places as our f's, which is kind of easy to do, right? If you have your u, v, like velocity components, temperature in these points, then fluxes are also easy to compute in the same points, right? And also, if you have u and v in the same point, it's very easy to compute Coriolis force, right? Because uv is right there at the same point as u. You don't need to average or interpolate anything. So, so we, for simplicity, let's use just second order interpolation. In this case, you compute, for example, f along the AB as just simply everywhere is the same, and equals as average 1/2 of f fij plus fij minus 1. So basically, this is our, would be our f grid point I j minus 1. This one is I plus 1j, and so on. So basically we say that f in this along this line equals just constant everywhere, and it's computed like this value here plus this value divided by 2. So average of these two values. Kind of logical and simple. So this is how we define FAB, and GAB also the same way. It's 1/2 GIJ plus GIJ minus 1. And so we can estimate for F along the BC and CD the same way. Now delta. Delta X along direction AB. And here this is why the direction is important here. Along the AB, so you see we're moving this direction. So X is delta. So it's one value minus another value. So I need to take X at B minus X at A. So this is our delta X. And those X's, those are coordinates. We know them. When we generated grid, we may pre-compute those values. So we know those coordinates of this point and no coordinate of this point. For example, we may just take all these 4 coordinates in this grid cell corners and compute average coordinate, which is like going to be the coordinate of this corner of this grid cell. So delta YAB equals to YB minus YA. So again, it's very important. Like for example, delta X for this one, delta X along direction CD equals to this minus this, because you see this direction you take of kind of downstream value minus upstream value. So it's XD minus XC. It's very important. Otherwise your sign will be wrong. Because some values, when you evaluate this integral, some value can be positive, some negative. So some values, these sub-integral kind of values will be edited, some will be subtracted to get this correct integral. So this is important to make it correct using this direction. Okay, so now you can actually write this statement as Aij dFij average dt plus FAB. So we take this one. So FAB delta YAB minus GAB delta XAB plus FBC delta YBC minus GBC delta YBC plus CD delta YCD minus GCD delta YCD and plus FDA delta YDA minus GDA delta YDA. And equals to GIJ area IJ. So that's it. So this is basically our scheme. So you pre-compute this dy's, dx before actually running your time loop. You can use for time, you can use your favorite time scheme. It can be leapfrog, for example, so that your right hand side would be evaluated at time step n and n minus 1, or for leapfrog it's only n, but you can use Adam's Bashforth scheme. Then this right hand side will be evaluated at time step n and n minus 1 and n minus 2 if it's third order Adam's Bashforth, and so on. So I don't specify this particular time derivative in this case. It's all depends on you, which time derivative you use. But your kind of derivative in space, all your terms in space, we approximate it like this, very simple algebraic equations. So just basically the summation of all these fluxes. And the fluxes can be easily computed. So let's see. So it doesn't actually look like, in a way, like, it doesn't really quite look like finite differences. So it's some kind of, just some, we replace all these derivatives with some summation of some, some intervals multiplied by some fluxes. So let's, just to see if it's actually consistent, let's let's check which expression is equivalent if we have regular grid that actually aligned along our coordinate system. So let's say that grid aligned along x and y. So we have like grid like this. In that case, our grid cell is going to be like this, and we have this normal coordinate system. So you see, in this case, what we have? Well, okay, let's plot here. So this is again A, B, C, D. So now this is x direction and this is y direction now. So now in that case, what we have, that delta x AB equals x and b minus x and a. So it's completely okay. Or it's equal, like for example, if it's same grid spacing in all directions. So let's say here is delta delta y, delta x. Normal kind of grid spacing everywhere is the same. Then it's equal just delta x. And delta YAB, what's delta YAB? It's y is the same along AB, so it's 0. And say delta XBC or CB, use here CB, actually BC, okay. BC equals to x at B at C, well, important, we see, this is direction, at C minus x at B. But x's are the same along this thing, so it's actually 0, and delta YBC equals to YC minus YB, which is equals just delta Y. So if you now substitute these guys into here, we'll see that some terms will disappear. And actually, if you do some algebra, just you will arrive to the following equation, that Fij dt plus Fi plus 1 minus j minus Fi minus 1 j divided by 2 delta x plus g ij plus 1 minus Fij minus g ij minus 1 divided by delta y equals to f to g to gij. So we will arrive to normal finite difference expression of this equation in flux form. This is what we considered when we, the same equation, similar equation we considered when we talked about conservation. So this is just equation, this equation, written derivatives written with second order accuracy. It's like fi plus 1 minus fi minus 1 divided by 2 delta x. This is central differences. So we just approximated derivatives using second order approximation in space. And so you see that this method, finite volume, if you use regular aligned grid, it just collapses, as we saw in one-dimensional case, to just finite difference scheme. But of course, this is only can be written if your grid is aligned along those axes, so that you could easily evaluate these derivatives. In this general case, when you have this tilted grid, this is what should be used. And this is finite volume scheme. So this is finite difference scheme, finite volume scheme. So for a regular grid aligned along x and y directions, actually finite volume method is equivalent to finite difference method. No advantage basically, but you cannot use finite difference method in more general case, of course. Another point that I would like to make about this, you see now this scheme is equivalent to central differences. So now we remember that if we use central differences in space, we cannot use earlier scheme in time, because in that case, that scheme, advection scheme, because those f contain these advective terms in them, it's unstable. It's unconditionally unstable for advection. So you see that we cannot use this Euler scheme, and so we cannot use Euler scheme for this too, because this is basically just more general form of this. If this one subset of this system is unstable for Euler scheme, it means that this one is also unstable for Euler scheme. So basically, in order to use this scheme, we need to use similar stability criterion applied for local grid spacings as before. For example, local current numbers should be, if we use certain scheme, like say leapfrog scheme, if we use leapfrog scheme, then for this time derivative, then and here is just would be central differences, so it would be stable for one dimensions for current number smaller than 1. For 2 dimensions, it would be current number divided by square root of 2. Remember that when we talked about stability in 2 and 3 dimensions. So we would then apply it locally. So locally we would have the stability criterion based on these spacings, actual spacings, the x, delta x and delta y. So we need to kind of keep that in mind, that the fact that we move to some finite volume method doesn't mean that our stability criterion don't work anymore. They still should be applied the same way as if you used a finite difference scheme instead of finite volume scheme. Although evaluate stability becomes a little bit more tedious in this case. Another advantage of finite volume in this form, first of all, the biggest advantage that it's very easy to evaluate all these terms here, like and also very easy to evaluate this delta x and delta y, because they're all computed on the same kind of using the same coordinate system. So another advantage, like that it's not necessary to have cells all like with the same number of corners. For example, we can, for this method, so for example, we could consider grid like the following, like maybe part of the grid uses triangles, and part of the grid actually a rectangle, and maybe here you may squeeze some pentagon in here. And here we can maybe use again a couple triangles like that. So we could have grid like this, and we're still able to use this method, because all we do is to compute this for each cell, we know area, we define some middle or average, and again, this is only notation here. I put these points. It doesn't mean that your value of f is actually in this point. It's actually in the whole cell, because we define just average of the whole cell. So this is our cell. This is values of f, and values of f and g computed in these cells. And for averaging, we can of course assume that this is like when we compute this. So we need to actually then come up with some scheme how you compute this average in this case when you have very kind of non-uniform grid. So we need maybe some area average, like area of this cell and area of this cell. So when you compute value of f or g in this along this edge, instead of 1/2 here, you use some area average. So this contribution of this cell into this value would be smaller than or larger than contribution of this, and so on. So you could use various forms of interpolation, and this can be a little bit tricky and depends on your creativity, how you would approach that. And some other factors. So like one of the, but see, when we compute this integral, we just basically compute all this. So for this pentagon, it's going to be 5 terms like this, 5 for f and 5 for g. And for this guy with 4 corners, it's going to be 4 terms like that. But conceptually, it doesn't matter. Like for each cell, regardless of number of corners you use or number of these sides of each of those figures, you can of those cells, regardless number of edges, you can use the same method. So that's the beauty of it. So it's completely all very distributed, and from programming point of view, it's very simple to do. So another point that I would like to make, that how about conservation? So this is very important property, right? Conservation of f, let's say. In that case, it's basically automatic. It's automatically conserved in this method. Why? Because you see, like when you add these f's multiplied by area, so this f times area, then it's only these terms. And you can see that here, like for example, this neighboring cell, it also should be counterclockwise. So now you see that when you add this expression, like f times its area plus f in this cell times area of this cell, then it's going to be only these terms. And these terms, f's are going to be the same in neighboring side for this cell and for this cell, and times delta y and delta x are the same except of the sign. Because you see here, you have direction in this, like you have in this direction, and here you have in this direction. So your, say, if it's A and this is B, then for this cell, delta, so let's say this is cell ij and this is cell I plus 1j, then delta x for I plus for ij cell equals to xb minus xa, and delta x for cell I plus 1j is going to be actually opposite, xb minus xa, because you need to follow this direction. So if you now add all these equations for each of the cells, these two directions will cancel out. So these terms will automatically cancel out for all edges of all cells. Only boundary edges will remain. And if you have periodic domains, then everything will cancel out automatically. So for finite volume method, the sum of all I and j's of this f times area, and this is important, times area equals to 0 automatically. Or if you have right hand side, it's going to be just of j, i, j, a, i, j. So it's a complete conservation statement. So all these fluxes will basically cancel out. So that's the beauty of finite volume method. You get conservation just naturally and for free. But it's concerning conservation of F, or for example, if it's U, for momentum. But how about kinetic energy? Remember variance? Then it's tricky. It's not automatically would conserve you. It would depend how you actually parameterize your F's along these boundaries. And that's beyond scope of this lecture. This is what makes it much trickier to design such scheme with such F's and G's that your variance is also preserved. And that can be very tricky. So that makes it a little bit much more complicated to actually conserve variance as well. It's not automatic, it's not just given. You need to be careful how you actually compute those F's and G's along these edges. Okay, before we move on, let's talk about one practical aspect of finite volume method, which is how you compute area of all those polygons that we can generate, like triangles, quadrilaterals, pentagons, or whatever. You need to some formula, easy way to compute those areas. So let's say that we have some arbitrary shape or polygon like this, and we assume that we know the coordinates of its corners. So it's from 1 to n. So in this case n is 5, but if it's triangle it's 3. So we assume that we have coordinates x, I, y, I, for I equals from 1 to n. And also we assume that, well, it's from this we see that x n plus 1 equals to just x1, and y n plus 1 equals to y1. We just will need it when we write general formula. So it's like basically like almost like periodic domain. So so for that we actually to compute this area we use again Green's theorem. So basically we use again that this double integral for area equals integral dx dy, so there is no function now here, and equals to what? Well, let's so here in Green's theorem, let's write Green's theorem again, that this integral, double integral of df dx plus dg dy dx dy equals to contour integral of f dy minus g dx. So now area equals to, so this is integral over area A, it's just double integral dx dy over area A. So this is what area. So if you compare this with that, what we see, we can actually have 1 here instead of this, say, function g. So we assume that g equals to 0. So we throw away this term altogether. Now to make this f, to make it 1, this guy 1, f should be equals to x. So that dx is 1. So this is our, in this case, our functions f and g. So using Green's theorem, we see that a equals to this contour integral f, which is x dy. That's it. So how we now use it? We cannot just approximate things. We need to compute it precisely. Well, for that, a common method to evaluate contour integrals like that along the boundary is to use so-called parametric representation of coordinates. Like, for example, so this thing for our case equals to, this integral is just integral along these straight lines. Those lines are straight between these coordinates xi and yi. So our area will be equal to sum from 1 to n of this integrals of x along this. So this is call it I equals from 1. So it's like x I dyi. So we will use parametric representation that our x, let's not use, just it's implied, I. We, this x along this direction for say one of those lines equals to, x equals to xi plus xi plus 1 minus xi times some parameter t. This parametric t, so which is changing, t is from 0 to 1. So we see that when t equal to 0, x equal to xi. Like for example, here is xi. Here is xi plus 1. This is yi plus 1. So when t equal to 1, then you see xi will cancel. It's going to be xi plus 1. So works fine. And y equals to yi plus 1 minus yi times also t. So this way we basically now replace this integral with integral. So integral of x dy becomes integral of x, which is xi plus 1 minus xi t times dy, and dy of this is, it's like d in this dt, so this is constant, so it will disappear. So we'll have times yi plus 1 minus yi dt. So now we reduce this integral to this, well, not reduce, but expand it into this integral. So now we can integrate it, and integral is from 0 to 1, right? Because t is changing from 0 to 1. So it becomes, let's see first this guy. We have x. So we have this y. This is just constant. We take it outside. And here we have x dt integral, so it becomes xi t plus xi plus 1 minus xi t square over 2, and this is evaluated from 0 to 1. So I just integrated t. So the integral of this x dt is just x t. Integral of this guy times t dt, and integral of t dt is t squared over 2. So now let's substitute. We have yi plus 1 minus yi. Now we substitute t equal to 1. It's xi plus 1 minus xi times 1/2. And if substitute 0, this whole thing disappears. So, or another way to write it, it's yi plus 1 minus yi times this guy is just xi plus 1 divided by 2. And so area is just sum of all those terms for different i's. So we see that our formula for area of arbitrary polygon equals to area equals to sum I equals from 1 to n of x I plus 1 minus xi plus xi times y I plus 1 minus yi divided by 2. So all we need to do is to know these coordinates, and that's it. We can compute our area. It's kind of cool. It can be further optimized a little bit by noticing that if we multiply those two together, we have sum 1/2, and here we have xi plus 1, y plus 1, plus xi yi plus 1, plus xi plus 1 yi plus xi yi. Now remember, this is like summation of a periodic domain. And remember, for periodic domain we can add 1 to indices, and with some, somewhere minus. Here is minus, iy, yes, here is minus 2. Yeah. So now if we add 1 to this, then these two guys will cancel out because they have different sign. So we have the following formula to n of 1/2 xi plus 1 xi yi plus 1 minus xi plus 1 yi. Just sum of this is equals to area. So very simple way to compute areas of irregular shapes.